Let's begin with a very simple demonstration to illustrate Amonton's law, which says that the pressure of a gas at a fixed volume is linearly related to temperature. Here, we have a steel sphere filled with gas and connected to a pressure gauge. And here we have a bath of ice water and one of boiling water. We know that ice water has a temperature of about 273 Kelvin and boiling water 373 Kelvin. Since an increase of 100 out of 300 Kelvin is about a third, we should see the pressure increase by about 1/3 as we transfer the sphere from the ice water to the boiling water. Looking at the pressure gauge, we see that it is indeed increasing. And since we started from 13 pounds per square inch, we ought to get to about 17 pounds per square inch. And we're just about there. Now, if we plunge the sphere back in the ice water, the pressure drops again. Did you know that this was how absolute zero was first estimated? If we were to graph our pressure-temperature relationship, we could extrapolate our line backwards to zero pressure, and this could define absolute zero. Of course, Amonton's law is a special case of the more general ideal gas law, PV equals nRT, where the special situation is that we are holding volume and amount of gas constant. We'll be exploring the ideal gas law more in upcoming lectures and exercises. Our next demonstration is of Boyle's law. In this apparatus, we have a piston connected to a pressure gauge. As I press the plunger at constant room temperature, the pressure increases proportional to the volume reduction. Our final demonstration involves a test tube containing dry ice, that is solid carbon dioxide, capped at the top with a piston. If we immerse the test tube in a bath warmer than the dry ice, in this case room air, the gas expands and raises the piston in the syringe. A valve at the side of the syringe permits the expanding gas to escape so that this demonstration cycles. Thus, gas expansion with increasing temperature can be employed to do work, in this case, to raise a piston. We'll spend some time looking carefully into just how much work can be done and how most efficiently to extract that work for different combinations of temperatures, volumes, and pressures.